Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Lin Nie with us today. Hello, Lin.
Hello, everyone. Hello, Frank.
Let's see. And it is my September 3rd of 2024 as we record this. And I do believe it is Wednesday, September 4th, where you are. And where are you located there, Lin?
I'm now in Wuhan, China.
Very good. So, yeah, we're about as far away as we can get. Um, is it still summer in Wuhan, or is it starting to cool off, turn into fall?
Yes, it's a summer day, sunny day, and it's very hot outside of the house. So we
Okay.
must sitting in the room and turn on the air conditions.
Yeah, yeah. So I'm in Phoenix. So I'm in a desert, and so we probably got just as hot as maybe you did today. So, but it is starting to cool off a little bit. It's a little cooler in the morning, so we're getting there. We're getting there. Very good. Uh, let's see. And Lynn, what do you like to do for research?
I'm now mainly focused on the weak lensing study, basically based on the PSF modeling and the galaxy shape measurement.
Cool.
Yes, and I'm now doing the PSF modeling work for the CSST, the
Oh yeah.
Chinese Space Station's telescope.
Huh? Very cool. Very cool. And that is going to bring us to this very lovely AJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. HybPSF, hybrid point spread function reconstruction for the observed JWST NIRCam image. And Lynn, take us away.
Okay. Okay. As we all know that the JWST give us unprecedented chance to study our universe, because after the first release of the JWST data, amount of works focused on the new data. So because for me and myself, my my study focus on the weakness study, and also the images of this star cluster of SMARCS 0723 are also released in the first release. So
Very cool.
we want to do something about this data. So for the weakness study, we mainly want to do is to estimate or measure the shape of the galaxies, and then extract the shape distortions from the galaxy images, and then to reconstruct the matters or dark matters from the images.
Okay.
So we mainly focus, we care about the images. So this is back to the topics of our works. So the first thing we want to do is to modeling the PSF of the observed images.
Okay.
So Prof Guan Yuan is who is the PI to lead the project in China to restudy this object, and the third author Guo Liang is my supervisor when I was studying my PhD degrees, and Lei Wang is he's doing most of the image processing for such as bad pixels or cosmic ray pixels extraction and padding, pixel paddings. And Cheng Cheng is he is helping us to process the image based on the pipeline published from the Japanese officially. And the last authors such as Charlene or Jifan who help us to do many discussions and other help us to help to improve our works to be better. So
Good.
this yes,
Shout
this
out.
is our our
Team.
our teams. So because we as mentioned previously, we mainly care about the clusters, so class SMARCS 0723. So we downloaded the data, and we want to mirror the shapes of the galaxies.
Yes. Okay.
Because as you know, the shape distortions for the lens study is very weak.
Yeah.
So generally people are always for the space telescope people because the imaging situation is always unsampled, so people always measure the image based on the stacked or co-edited images.
Yeah.
But as we know, there are maybe some discontinuous or the camera distortions between different chips or different exposures.
Right.
So for the weak lens, because the signal is very weak, so we prefer to measure the shapes based on single exposure images.
If you can, yeah.
So this is the motivation or the reason why we do or why we report a new method for the JWST images.
Cool. Very cool.
Yes,
Okay.
yes. So we first, as we go into the second section, we started to do our data reductions.
Okay.
So so we first download these single exposed images and doing some basic reduction based on the official software, such as remove the 1/f noise or the other detector effects. And then we use the multiple exposure images to check or verify the cosmic rays, and then cutting these pixels by combining the multiple exposures. And they finally our modeling, our processing images is started based on the processed images. Cool. And we first extract we want to modeling the PSF, so we need to extract the star images from these chips. So with the first thing we use Sextractor, which is the generally used tools to do these things from the images. So now we're going to the figure 1. We use the parameters measured in Sextractors, such as full width of half maximum and the magnitude.
Yes.
We can plot all the source on this parameter space. We can see that the stars or these point source are obvious lines at the bottom of the images as a line, because they have very similar the size or the FWHM. So we can extract the stars from the bottom star looks as shown in figure 1, and I pointed this source stars out as the blue stars as shown in the images. So yes. Yes, we indeed, but we also encounter some other problem or challenges for the star modeling as we go into the second picture, figure 2. When we extract these star images from JWST, because we know it look at the near frame band, so there are many source would experience in the images. So we can see the upper panels in the figure 2. We can see that there are many neighboring sources near the stars. So this is a challenge for do PSF modeling. So we have did we have did an amount of tests to we want to excluding the neighborings. So as finally we found that we can use the FOF friend of friend algorithm to identify the isolated object in such as small stamps, and we exclude those objects who lines far away from the center of the stamps.
Okay, very good.
So very good. Yes, and now we can use the deblended star stamps to do the further object.
Okay. All right.
Yes. Yes, obviously the JWST official provide us a tool to generate the PSF models. I mean the web of PSF. We first we want to check the precision of the PSF model, and between the model and the data. I mean the star images. So we use web of PSF to generate the represent the corresponding PSF models according to the images. I mean such as the exposure time, the pixel position, and the detector of the images. All these parameters can be input in the web of PSF.
Yes.
And yes, and the result is all the difference between the models and the images is shown in figure 3.
Okay.
Yes.
2, I'm good. And figure 3, and here's
this is an example of the residues, because we have used three bands from F0902 to F444. This just the examples.
Yes, understood.
I remember that the first time I've make this residues is about middle of 2022, and the web of PSF is I mean is at the now time is an old version. We can say the residues from the improved version, still we can see some structures left in the residues. At that time, the residue is much more obvious, and I mean it's more the model is it's much more worse. So at that time, I saw the structures, and so I mean I want to do the first thing I know that the web of PSF maybe is not good enough for measure the galaxy shape. So we need to do something.
I'm with you.
And and the second thing I have done is to looking for some traditional method to construct the PSF models that we can use to do the further work. So I then used an modified or improved PCA method, principal component analysis method, to construct the PSF models,
Yes.
because PSF is generally used for also for ground-based or space-based telescopes.
Yes.
So yes, and we found that I did use the InPSF, but as we can see in Figure 4,
Yep. I was going to say we go
I
there.
I compared the shape parameters such as ellipticity component 1, component 2, and the relative size residues between the model and images. We found that the either the scatter or the mean residues goes up to 10 or more percent. So
Yes.
we know that this precision is cannot be used for shear measurement.
All right.
So this is the problem. So and another thing we're gonna to think about other method. But as we can see, the structures, the PSF structures as shown in Figure 2 is for JWST is unique. It have very complex structures and
Oh yeah.
yeah.
You too.
And
Here we go. Yep.
and they yes. Yes,
Okay.
and and another reason is we can see shown in table 2.
Table 2. Let's see, where did I get that one? Table 2, mean number. Here we go.
Yes, table 2 represented the properties we extracted from each detectors and each band subband. So as we can see, the upper regions shown the module A, which I mean the JWST have two area for two different series detectors. They named module A and module B.
Okay.
So for the short wavelengths such as F0902, F2000, they have four chips for the module A area and for the module B area. But for the long wavelength band, they have two big chips.
Yeah, right.
And we can see this is configured as in the second columns. And for the third and the later columns, they show the mean star number extracted from our previous process. We can see for the short wavelength, they have only about 10 or 12 stars. That's pretty few. And they left in each column, the left side shows the FWHM of the star images. Some of them is smaller than 2, which means the star images is undersampling. So yes. So basically for general PSF modeling, people always first thing is to interpolate the star image to align the center of the images to the same point and do the further analysis. But for the undersampled images, we will say the alignment problem from this kind of images. This is the first thing. And the second, we can see the star numbers is very few. And also a third reason is that we can see the FWHM for such as for we can choose for H such as for example for H150 for module A, the mean FWHM is smaller than 2, but for the module B, the FWHM is larger than 2. So this, which means the PSF properties for different modules are also changing. So So I mean, if you want to measure some very weak signals, you need to consider the difference between different chips. So our strategy is to modeling the APS models in each chips for every exposures.
Yes. Good. Good.
Yes.
I'm with you.
Yes. So back to the figure 3, we
Sure.
can see the residue structures of the structures of the residues have some similar or correlations.
Yes.
So maybe we can do some strategy to extract these correlations to add these residues back to the WebPSF model.
Very good. Okay.
And to compose a better model. So this is the basic idea for our work.
Got it.
So but the problem is how to achieve it. So yes, so we can do it go into the equation 2.
Sure.
Yeah.
Equation 2, slide down. We got equation 1 there. There's our E's and R's. And equation 2 is right here. PCA.
Yes, by considering the similar or correlations of these structures residues, so we can try to use such as PCA or some other kind of method to modeling or reconstruct the residue structures and add it back to the WebPSF. So this is the equation 2 shows the basic idea of this this work. So as you know, if we want to do PCA with the first, then maybe for the traditional side, we need to interpolate the center of each residue to the same position. But as talked previous, the images are undersampled, so we cannot do that.
Right, you can't find them. Yes, agreed.
So the solution for this work is to use the priori modelings such as parameter modelings to model the structures.
Okay.
So yes, from my previous work, which is published in 2021, I used the function morpheteless basis functions as which is I can find it's in the upper 4 lines at equation 4.
Here we go.
Yes, here. We found that we can use the morpheteless basis functions to construct very complex structures. And yes, we in this work so I used the same process. We want to use morpheteless basis functions to construct the residues.
Okay.
And yes, this is this idea or this process is shown in equation 4, but we did not use these functions to fit the residues directly. We use the basis functions to construct the principal components rather than the images itself, because we can get much more concentrated components.
Yes. I'm with you.
Yes. Yeah. So finally, we got a model for the residue structures, and another model is coming from the WebPSF, and we combine the two structures together to compose the final PSF models, which is shown in this work. We call it HybPSF because it's a hybrid.
Right.
Which comes,
kind of extra twang to it. Very good.
Yeah. And another small things I want to talk about is we also tested try use any other kind of basis functions such as Gaussian layers or shapelets.
Okay.
And yes, and finally we found that from this basis function we found that Morphet has the best
Better.
performance.
Okay.
So yeah, so we
Unfamiliar
use
with it.
Morphet
Gotta
in this
say.
work.
Okay.
Yes.
Cool.
Another advantage for this this work is that we can combining weight function in the chi-squared minimizer as also shown in equation 4, because we have mentioned that
Yeah.
there are some areas the neighborings are removed. So
Uh-huh.
the left areas we mask as zeros.
Okay.
So for
That will just
these
count.
pixels, we can give it the weight values can be give it as 0 in chi-squared minimizing. So
Okay.
this much more convenient to
Yes.
do
To
the modifying. Yes. And also the pixel noise can be considered in the weight function too.
Yes. Uh-huh.
So the examples for the HYPSF residues is shown in figure 5. We can see that the
Ooh.
yes the
Yeah.
color bar
Much better.
the color bar of the residues is going to about several thousand. Yes. So we can see that this is
Very
indeed
good.
improved, and the structure shows showing less correlations. So we can
Okay.
we can see that this is indeed improved. But for weakness, we more about the shape precisions. So we further doing the shape comparisons for the PSF models and the star images.
Okay.
So this the first comparison is shown in figure 6.
Okay, I'm with you. Figure
Yes.
5. It's constructing the hybrid, PCAs, NIRCams, and figure 6 ellipticities. Okay.
Yes. The left panels shows the ellipticity made from the star images. Star image
modules.
For at different positions for the both of the two modules. And the center panels show the ellipticity from the two kind of models, which for the red line is from the HYPSF, and the blue bar is from the WebPSF. We can see that the ellipticity for the both of the two methods is much is very similar to the images.
Yes.
And yes, and
residual.
and at the right panels, which shows the shape residues, especially for ellipticity. For HYPSF and WebPSF, they have shown the similar behaviors in the residues. So we can say that the HYPSF and the WebPSF can give very similar results.
Yes.
So another shape for size, we also want to have a look. So let's go into the figure 7.
Yep. And we're gonna do. Okay, we're gonna do
let's
once. These are the R's over R.
Yes. Yeah. Let's see the right 3 panels first, because it shows the shape the relative size residues from the two different methods. We can see that the blue histogram is from the HYPSF, and the blue histogram is from the WebPSF. We can see that the distribution, the center of the two distributions is obviously different,
Yeah.
and the red regions, the center of the red regions is very close to the zero. This is what we exactly
That's what
wanted.
you want. Yeah,
Yes.
exactly. Right.
Yes. And this figure shows
Right.
the
Cool.
shorter band of the NIRCam. So we can see
Okay.
all of the 3
90.
band from
Yeah.
19 to 2000 all shows the similar changes or improve from HYBPS.
Indeed.
So
Very good.
yes, and we also can see the distribution of the residues is like the Gaussian. So we can also say that the model of HYBPS is, we can say, it's unbiased because the residue is shown like
Is the
Gaussian
Gaussian.
distribution.
Yeah.
Yeah.
Right. Poisson.
And for each color, they have deeper and lighter regions, because
Yeah.
this is why, because we know that the star images we extracted from each exposure is very few, and we also checked the signal to noise ratios of each images is also very, very small. Only about over half of the images less than
100.
40
Okay.
less than
Okay.
40. So
Okay.
it's so maybe the scatter of the distributions we think maybe it's not only from our model but also from the noise from the images.
Yes.
So for the deeper for the lighter regions, we use all samples from all the extracted samples, but for the deeper color, we used only those images which have SNRs larger than 100.
Yes.
So we believe that is pretty high, and the noise can give less contaminations in the results. So yes, indeed, as shown in the figures, the
That's
deeper
awesome.
regions shows much more concentrated distributions.
Cool. Yes.
Yeah.
Tighter.
Yeah.
Yep.
And similarly, this is for the shorter band. For the long band, we also do the same comparisons. We can see that the size residues from HYBPS is also improved.
Okay.
Similarly as the short wavelengths.
And
as also shown in the
definitely works.
ellipticity comparisons, we can see some that such as, let's see, for example, let's see filter 20, the first elliptic component. We can say that yes, the ellipticity residues, the center of the blue histogram is also near the 0 point, but from HYBPS it's shown much more concentrated distributions. So we can show this is also an improve for HYBPS.
It's working very well.
Yes, so we were glad to have this improvement. So and finally, we also plot some comparisons that we want see the 0 point or the scatter range of these residues, such as shown in figure. Let's see in figure 9.
Figure 9. Let's go to figure 9. Yes.
Yes. Figure 9 shows the statistical results of the residues from the two methods, and also the blue points and red points come from WPSF and HYBPSF correspondingly. We can show that especially for the size residues, HYBPS obviously drag the we can we can think it will drag the blue point back to the 0 point, back to 0,
Very
and
good.
also have more shorter error bars, as you can see at the right panel of
Oh yeah.
F2000. Yes.
Uh-huh.
This can be directly shown that this for our
Very
method
cool.
is, yes, it achieved all the first goal.
Beautiful.
So yes, so we did some further analysis as shown in table 3, because we care about the value or the number of the precisions. Table 3 shows the mean of the residues and the scatter or the width of the distributions. Both for the upper side of the panels shows the results from WebPSF, and the lower regions from HybPSF. And we can see even for the mean of the elliptic residues, HybPSF can going down to several point thousand rather than for the HybPSF, and for WebPSF it's yes, it's several thousand. So it's we can say it's literally magnitude of improvement.
Correct.
For HybPSF. Yeah, and for this, yes, and for the scatter, it also shows the similar conclusion. For WebPSF, it's several percent, but for HybPSF, it's going to going to 1,000. And also, as shown in the previous figures, the most difference is shown in the size comparisons.
Yeah, delta over R.
We can say for HybPSF, even for the mean, it can go for 6 or 7%, but for HybPSF, it can go to several down to 1%, down to 1%.
Very good.
So
very good.
Yeah. So from this result, we can think we maybe can use these modelings to used in the further work such as the galaxy shape measurements and or further analysis. Yes, and table 4 is for the co-added image analysis. I mean, which is another proven that the HybPSF indeed can improve the models. And another point I think is a little bit important is for our model is that not only at the inner region, because as you can see, the star stamps extracted from the star images is relatively small, and the star spikes, which show the diffraction pattern from the telescope is it's not that much, because we can see in the original data the big images released from JWST. Several stars have very extended structures induced from the diffraction effect. So yes, let's go to figure 11.
Yes.
I mean, for the shape comparisons, we concentrate at the inner regions of the PSF, and because one part of our model is from the WebPSF. WebPSF can also give us the outside structures of the PSF model. So we do some comparisons from the real data and our models. So for this figure, we extract a relative very large areas. It's about 200 times 200 pixels, and it's very large.
Ooh,
Yes,
okay.
we can see the left panels show the star image extracted directly from the data,
Huh.
and
Good spike.
the yes,
Blue stuff up.
the middle and the right panels is shows the residues which is subtract the PSF models from the two methods.
Yes, I'm with you.
Yes, yes. Yes, we can see the result. We can see for the upper panels, we can see that this spider structure or the diffraction structures is indeed subtracted from our models.
Yeah, very much
And
so.
at the lower regions, we can see that we can compare the two residues. We can see that the residues from HybPSF is show much more noisy than the WebPSF. We can say this is not only for the small objects, small PSF models, but also for the very big. If you want to use very big PSF models, we can also get an improvement.
Nice.
Yes.
Lovely.
Yeah, and little tricky is for this figure is that we did many tests to calculate the flux of the stars, because you can see there are also some neighborings because the image is very large. So
Yeah.
we indeed have. So we actually circle a region at the inner of the stars, and we match the flux of the data and the models.
At that point.
Yes, and then subtract the models. So
Okay, gotcha.
yes.
Cool.
Yes, this is I think is almost the results and the most important things in our work.
Beautiful.
For this work.
Yeah. Beautiful. Very nice. Very
Thank you.
nice.
Thank you so much.
Thank you. That was really cool. Very nice. All right. Lin, I want to thank you so much for walking us through your very lovely article. Awesome. Let's see. So
My
you kind of
pleasure.
hinted at it a couple of times. So let me ask, what do you think are some of the next steps to maybe actually apply this to some clusters? Are there additional subtractions that could be done to make the PSF even better? Is this going to be adopted by JWST as sort of the default PSF? And so where do we go from here, given the published article?
Yes, you are exactly said right. We are now doing the galaxy shape measurement based on the modelings, and we indeed see some signals from our results, lensing signals. And now we are doing some further analysis from the source analysis, because there are only a few objects can have spectroscopic redshift, but at the left, most of them only have such as photo Z or other redshift informations. So we are doing this, and for this model itself, we indeed consider another method for HybPSF, because we can see for the residues, we can look at the residues for HybPSF. It also have some structures left it.
Yes, we saw that.
And some of them is from coming, such as ring features. Is coming from the is coming from the basis functions. So we are now develop unparameterized method, but also PCA, but it's super sampled. It can be super sampled.
Okay.
Parameterized PCA method to construct these structures.
Very good. Very cool. Very nice. Lin, thank you so much. Be really great.
You're welcome.
It'll be really fun to see this develop over the next couple of years, and the applications of it to some of those clusters will be very cool. Very nice. Thank you.
Thank you too.
And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Bye bye.